overview of what is an encoder, the input embedding layer, the position encoding layer, and what are there are set of 6 layers, and what does these 6 layers consist of, which is a multi-head attention system and also a fully connected network, right? So now today we'll be looking more into the in-depth of what exactly is there into this encoder network, how that actually works, and what are the things. Okay, so but before that I would like to tell you more about this. No, attention. What is attention? I told you that attention is all you need is the name of the paper. So why attention and what is attention? So this attention you saw, there's this attention block. Okay, there was this attention block in this encoder, right? So that attention block, what has it done? So the attention block is basically trying to find the word to word relationship. It's a word to word operation. It tries to find what is the word to word relationship between all the words or the tokens that you have put in. We saw the previous example, this example, wherein we are trying to find the word to word relationship between all pairs of words possible. This same thing is attained, this same thing we reach using this attention. Okay, so attention is basically has replaced the recurrence function. Why was that important and why is that a big deal? Because in the recurrence function, which is used in the RNNs or in all NLSTMs and all, the main drawback was as the sequence of the words increase, as the number of words increase or the distance between two words increase, say the and mat. So there's certain number of words between this and this. So as the number of words increase, the number of parameters also increases, and which is one of the problems because here it doesn't try to find the relationship between the tokens directly. It tries to understand the whole or analyze the whole sentence. Okay, but that's not the case with the transformer network. Okay, so the attention mechanism, so just need to find out how each word is related to all the other words in a sequence, and also including the word itself. And attention it basically runs a dot product between the word vectors and determines the strongest relationship of a word with all other words, right? I told you that if two words are close enough, and then the word embeddings, the dot product will tell us that what are the words that are pretty similar. Okay, and all these attention sublayers are actually parallelized so that it is faster, and that is why this process is known as multi-head attention. And as we know that there are a total of 6 layers, and all these 6 layers will like this is the layer 1, then there would be a layer 2 and then layer 3. All these 6 layers learn different perspective of same input sequence, right? So that is what makes it different from RNNs. So that is something about the attention mechanism, and which is very important and a very important component of the transformer network. But that is not the whole thing. There are more critical things into the transformer that we will be looking at later. So okay, so now let's deep dive into the encoder stack and what does the each layer do. Okay, so as we know that the encoder stack consists of 6 layers, and we also saw that there is skip connection in encoder layers. That is the output of um, that is this whatever is the output, this the output from this multi-head attention also goes into the addition and norm, and also there is a skip connection. That is, it takes the input from here and also passes it to here. So basically it is like layer normalization of x plus sublayer x. Okay, so if we see here, this layer normalization takes input X as well as the output from this sub layer which takes input X. Okay, so this is how this the input flows from different layers, and that happens for all n is equals to 6 layers, right? And also we know that this multi-head attention, they are same in all the 6 layers, but they do not perform the same operation. They do not perform the same task. They perform the same operation, but they do not perform the same task. What does that mean? Because each takes different input and thus try to understand or associate words in a different perspective. In a similar way, how we try to associate different letters and words in a crossword puzzle. Right? It's a very similar fashion. Also, in the last video, I told you that the dimension of the model on the original transformer paper. Remember, it's this we are talking about the original transformer. We can even change the value of D model. So for the original transformer, the D model was set to be 512, which is the output dimension for each layer would be 512, and this makes it very powerful, and it has a very powerful consequence because all the operations are practically the dot product, and as a result, the dimension will remain stable and also reduce the number of operations to calculate, and also the machine consumption would be very less. So thus, if we see the encoder, it is very highly optimized architecture of the transformer. Okay, so this was about the encoder. Now let us start off with the layers. Okay, let's start off with the very first layer, which is input embedding layer. Okay, what is the input embedding layer? Okay, so for the input embedding layer, it just takes the input tokens and converts them into vectors. Okay, it's basically it takes the input tokens and convert them into vectors of dimension D model, which is equals to 512 as per the original paper. And how does it do that? It uses the learned embeddings in the original transformer model to do the conversion. Okay, like in this transformation, the tokenization, the um, to do this, to convert the input into tokens, there are many techniques to convert these into tokens. Okay, however, in the original paper, the transformer initially used the BPE, the byte pair encoding. Okay, uses the BPE encoding technique, and there are other techniques such as the word piece or sentence piece, but for the transformer initially they went ahead with the BPE technique. Okay, so no need to go in depth how does BPE works. It's basically it tries to convert the whole sentence into say a cat would be converted into CAT, and then it will try to see what pairs of tokens are coming, maximum number of times. So certain scat, pat, mat are there in the vocabulary, then it would see that okay, 80 is coming a multi number of times, then 80 would become a token, C would become another token, P would become another token, M would become another token. So this is how it does the vectorization. So the whole so if the sentence is cat, pat, mat, so we can see that all this could be made from this particular vocabulary. Okay. So similarly, if we say that our sentence is the transformer is an innovative NLP model. Now if we pass it to the BPE tokenizer, we'll get the output as the we won't get this output. I'll tell you what output you'll get. Yeah. So this output you'll get for the BPE. I'll tell you the vectorized part of it is innovative NLP model. Okay, this is the output you'll get. But if you see that if this is the output of the tokenizer, then it couldn't be fed into, it could be converted into embeddings, right? Because it generally takes integer values as input, right? So the tokenizer will provide you the integer representation of all the words that you are wanting. So integer representation of this whole sentence will be would be like something, these everything will have a number like 1096, 1098, anything. So these would be represented by integers. Okay, so that is how this first part is done, that is the token. So this, the very first thing we are looking is here is input embedding, how it works. So out of that, the very beginning, the first thing, the tokenization. So this is how we get the integer representation of it. Okay, now after we get the integer representation, we see that there's not information in this tokenized text at this point, right? Because if we see, let's say let's take this let's take the example of the previous the thing that we discussed in the previous video, the cat and tiger. They both belong to the cat family. So in a way we want that the tokens of this cat and the token of tiger should be more similar as compared to tokens of cat and bat, right? Because these and this is a completely different species altogether. Uh, this is a cat family. This and this is a flying mammal, right? So this is a land mammal and this is a flying mammal, right? So this is what should be, and that is why that is the sort of tokenization or the embedding we need, such that there's a relationship between the tokenization, right? How do you do that? For this, for explanation, let us see into the skip gram architecture of word2vec. So I told you about word2vec. So in 2013, Google came up with word2vec. Okay. Now, in order to train word2vec, they use a technique called skip gram architecture. Now, what is it? The skip gram architecture just focuses on the center word in a window and predict the context word. Okay, so that is, it will analyze the word I minus 2, I minus 1, I plus 1 and I plus 2 to predict the word I. Okay, so that, and then it will slide, this whole window will slide by one step, and this will keep on repeating. So the skip gram model had an input layer, a hidden layer and an output layer. This output layer would contain the embeddings of the word I. Okay, so that is how it was. So you will feed in the embeddings of all the surrounding words and train the model such that it generates the embedding of the center word I. So that is how the skip gram architecture was used to train the word2vec embedding. Okay, so let us say that we have two words. Let us say it's brown and black. These two words are colors, right? So we want that the embedding should also be similar. So if we use the skip gram architecture of word2vec and we use the word2vec to generate the embedding, and the generated embedding is of the dimension of D model, which is 512. So let us say brown has an embedding um, like anything 0.095, 0.10695, 0.0256, and so this keep on going for 512 values, and similarly black is also somewhat similar, right? So we want that these two embeddings should be similar, because it should be intuitive from the embedding itself that these two things belong somewhat, are somewhere belong to the same family, which is here is color. Okay, so how do we know? We can find the cosine similarity these two factors. So if we find the cosine similarity, if we use the word 2vec to generate the vectors for brown and black, you can try that. So you'll get the cos, and then if you pass in whatever the vectors that you get, and if you pass in to the cosine similarity function of brown and black, you'll get a cosine similarity of somewhere around 0.9998, which says these two values are very quite similar. Okay, and thus you know that this is the very first layer, you know, right? And this tokenization and the input embeddings is happening here, the very first layer of the transformer. So we see that this very first layer itself, from here itself the transformer is not starting empty handed. From the very first layer itself, it is having the context of the tokens. What does this token mean? It is a contextual, the vectors are having a contextual meaning to these tokens, and that is where the transformer starts. Okay, but there's one more problem. Let us say that there's a sentence that we have: the black cat sat on the couch and the brown dog slept on the rug. Now you see black is coming at this point in the sentence, which is at the one index. And 2, 3, 4, 5, 6, 7, 8, 9, 10, and brown is coming at the ninth index, right? But if we see the cosine similarity, black and brown are very similar. But when we if we simply pass, which means if we simply pass these token values of all the words, we simply convert it into tokens. Let's see how many words are there total. 8, 9, 10, 11, 12, 13, 14, and let's say we have passed a matrix of 14 cross 512. Okay, this is the matrix that we are passing into the next step of the model. But don't you think that there's no information of where this word is actually positioned? If we find the pairwise, because we know attention network tries to find the pairwise relationship, right? Pairwise relationship between two words, but there's no information where was this word coming in the original sentence, and that could make a difference, right? So we also need to encode the positions of the word, right? There's only simple word embedding or word encoding, that's not enough. We also need to encode the position. That is where, if you see in this diagram, that is where this comes in, the positional encoding, right? So that is very important, and that we'll be discussing into the next video. So I hope that you were able to understand the very first point of the input embedding. Why is it important, and what is, even why is it important, more important, what does it do actually, right? Because it's the very first thing, and that we should have an idea of how does this input embedding thing work. In the next video we'll be talking about the position encoding, and it's a very brilliant technique that Google came up in order to encode these positions, and that too without making much difference into that into the tokenization, right? Because there's a constraint. We can't go beyond 512. There's a constraint. We can't go beyond 512. That is constraint number one. And that is another constraint, that even after the positional encoding, we do want that the tokenized value, or the vectorized representation of the word black should definitely be similar to the word brown as compared to any other word, dog or slept. It should be much more similar to the word brown. So these two constraints, how did Google overcome, we'll be talking into the next video. So thank you for staying, and happy learning.